Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 29, 2026, just about 6 days ago. It introduces a scalable framework called Mechanistic data attribution that traces internal model circuits back to their origins in the training data, showing that removing less than 10% of high-influence samples can significantly hinder the formation of key components, like induction heads. The paper is titled Mechanistic Data Attribution, Tracing the Training Origins of Interpretable LLM Units. And as we'll see later, the implications for controlling how models learn specific behaviors are quite significant. Figure 1 outlines the Mechanistic Data Attribution framework, illustrating how it connects model internals to training data across 3 stages. In stage 1 at the top, the system localizes interpretable units, like neurons or specific attention heads, using tools such as sparse autoencoders. Then, stage 2 computes the influence of the training corpus, applying an influence function to determine which specific documents shape those parameters. This leads to stage 3 at the bottom, which validates the approach. By identifying key data patterns like XML or latex, we can perform training interventions, augmenting or deleting that data to directly control how the model circuits develop. Alright, having outlined the framework, Figure 2 presents the causal validation across different model scales, ranging from Pythia 14M to 160M. The top row tracks the emergence of induction heads, while the bottom row monitors previous token heads. In these plots, the red line represents training, where the high-influence data was deleted. We see this consistently suppresses the head score compared to the baseline in orange, proving these specific samples are necessary. In contrast, the green line shows that augmenting this data accelerates the process, establishing a direct causal link. So while the previous figure confirmed that specific data drives learning, Table 1 reveals exactly what those high-influence samples look like. The table lists categories like XML, code, and latex, which all feature highly rigid, repetitive structures. Intriguingly, looking at the bottom row, even completely meaningless repetitive character strings act as strong catalysts. This suggests the induction heads are simply learning to copy patterns from any available repetition, regardless of whether the content makes semantic sense. Well, Figure 3 now analyzes the statistical properties of these high-influence samples. Starting with panel A on the top left, the cumulative score curve follows a sharp power law distribution. This means a tiny fraction of the data, the top 10%, contributes about half of the total influence, which explains why the small targeted interventions we saw earlier are so effective. Then, in panel B, the heat map demonstrates strong crosshead consistency. The dark blue block shows that different induction heads agree on which samples matter, proving the method isolates mechanism-specific data. Okay, connecting these data insights to actual capabilities, Figure 4 validates the functional link between induction heads and in-context learning. Across these 4 panels for Pythia 14M through 160M, the vertical axis tracks the in-context learning score during training. The solid red line reveals that deleting the high-influence data significantly delays the emergence of this capability compared to the orange baseline. Conversely, the green line shows that augmenting that same data accelerates it. Because these specific interventions were designed to target induction heads, this simultaneous shift proves that those heads are the causal mechanism behind the model's ability to learn in context. So, Table 2 explores if we can leverage these insights for efficient training. The authors generated synthetic data based on the small Pythia 14M model and applied it to larger models. The delta column on the right reveals consistent improvements across all scales. Most strikingly, compare the bottom 2 rows. The 160M model gains nearly 10% using the small model's data, but only about 2.6% using data derived from itself. This implies that the structural curriculum is scale invariant, allowing lightweight proxies to effectively optimize larger systems. Alright, for those interested in the implementation details, Table 3 specifies exactly how the framework targets each component. The first row details induction heads, using a prefix matching score to find them, and a copy-paste task to probe them. Crucially, the subspace projection includes all 4 weight matrices, query, key, value, and output, to capture the full circuit. In contrast, the second row shows that, for previous token heads, the analysis narrows down to just the query and key matrices. Finally, the bottom rows demonstrate how the method generalizes to MLP neurons and sparse autoencoder features. Wrapping up, 2 big takeaways stand out. First, this research proves we can trace abstract model capabilities, like in-context learning, directly back to specific training documents, often repetitive code or XML. Second, this enables mechanistic alignment, where we can deliberately steer model behavior or remove unwanted traits just by curating a tiny fraction of the data. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.